Okay. Good morning, everyone. This is Felix Landra. It's my pleasure to introduce our speaker today, David Weiss. David is a member of the Solar Systems Dynamics Group at JPL, which he joined 10 years ago in 2011, and I've been working with David ever since. Been a very fruitful collaboration. David is really a world expert in the optimization of gravity satellite mission design and data processing approaches. And it extends all the way to the scientific interpretation of the data. And most of you probably know David as the primary developer of the JPL MassCon solution, which is one of the most used GRACE follow-on data sets. He's a principal investigator on the GRACE and GRACE follow-on science team. He has authored or co-authored over 30 papers, including many community assessments. And for his work, he has received the JPL Lou Allen Award, as well as the NASA Early Career Achievement Medal. More recently, over the last year or two, he has focused his energy on the Decadal Survey Mass Change Designated Observable study, where he has served as the deputy study coordinator. And today he will report out on the findings of that study and kind of lay out the path towards the follow-on to GRACE follow-on. I think still need to work on the name for that mission, but really towards sustaining long-term mass change observing systems. And I'll turn it over to you, David. Take it away.
Okay, thanks, Felix. Let me share my screen. I want to introduce throughout the seminar today, you'll probably hear some very high-pitched sounds. So we have some neighborhood peacocks that I'll introduce right now. So everything's okay, but they tend to come through my AirPods. So let's see. Is it coming through fine?
Yes. Yeah, looks good.
Okay, great. So I'm going to report out on the Mass Change Designated Observable study. So first, everything today that I'm going to show is really the product of a very, very collaborative team effort between members at JPL, Goddard, Langley, and Ames. Bernie Beanstalk served as our study coordinator, and I think he's on the line today as well. And then also I want to give thanks to the GRACE and GRACE follow-on projects. There's several figures and animations in this talk that I'll use to explain certain concepts. So let me jump right in. So I want to start the story 25 years ago, because that's when it begins, when GRACE was selected under the Earth System Science Pathfinder program in 1997. And it launched subsequently in 2002 and lasted for 15 years. And that was really the establishment of the mass change data record. And we really saw the Earth in a way that we had not seen it before, looking at large scale mass transfer between the oceans and the continents, ice sheet mass change, et cetera. And the community, I think, quickly realized the value of these observations in understanding the Earth as a climate system. In 2007, the Decadal Survey that came out recommended a higher capability GRACE 2 mission that was slated to be a Tier 3 mission. And so already in 2010, then 3 years later, NASA put out a Climate-Centric Architecture report, and in that report it recommended GRACE follow-on as a gap filler to continue the observations between GRACE and then this higher capability GRACE 2 mission. So there was already a recognition that GRACE 2 was further on the horizon, and then we got GRACE follow-on launched in 2018. You can see there on the bottom right of the screen. And we ended up with a 1-year data gap between GRACE and GRACE follow-on. After the Climate-Centric Architecture report, there were 2 reports that are worth mentioning. In 2015, there was an IUGG, that's the International Union of Geodesy and Geophysics report, that really focused on establishing science and user needs for mass change products. And those mostly represented improvements relative to the program of record that GRACE and GRACE follow-on have established. And then in 2016, there was a joint working group between NASA and ESA that provided a roadmap for a 2-pair, kind of 2 GRACE pairs of satellites implementation to satisfy those user needs from the IUGG report. And then that brings us to the topic of today, which is the 2017 Decadal Survey, where mass change was recommended as a designated observable. So, the Decadal Survey, we know it's released every 10 years. In this particular Decadal Survey, there was a new class of observation established called the Designated Observables, and there's 5 of them. Mass Change is one of them. And in response to this designation, NASA initiated multi-center study teams for each of these. Aerosols, clouds, convection, and precipitation was combined into one study. And for mass change, that study was led here by JPL, but as I mentioned already, it included members from Goddard, Langley, and Ames. And so the backdrop of both the Decadal Survey as well as our study efforts are really this almost 20-year now time record established by GRACE and GRACE Follow-On, and all the amazing discoveries that have come from these 2 missions. And so there's really 2 themes that are prevalent that I want to hit on today in the talk. And the first theme is continuity. So this is a quote from the Decadal Survey where it says, mass change observations will ensure continuity of measurements of groundwater, water storage mass change, land ice contributions to sea level rise, ocean mass change and ocean heat content, and then GIA and earthquake mass movement. And then it also highlights the importance for operational applications such as drought assessment. The second theme that we'll talk about today is the quality of the measurements. So how can we improve relative to the program of record, if there is room to do so? And so just as a mental anchor point, when we think about how good measurements are or what the quality of the measurements are, we think about that in a 3-dimensional space in terms of temporal resolution, spatial resolution, and accuracy. And mass change data is a bit unique because depending on how we process the data, there is a continuum of solutions that exist in this domain of spatial resolution, temporal resolution, and accuracy. And depending on how we aggregate the data, we can get weekly gravity solutions or monthly gravity solutions or even yearly gravity solutions. And then the spatial resolution and accuracy change subsequently. But this is a standard anchor point, monthly resolution, 300 kilometer by 300 kilometer footprint, if you will, and an accuracy of about 2 centimeters equivalent water height. And so this is an overview of the study process. I'm going to use this as kind of an outline going through the talk today. But the study team started with the Decadal Survey on the left, and that was really our guiding document. We established a science and applications traceability matrix. We also identified a large trade space of architectures and technologies, and we had a method then that we assessed the capabilities of those architectures against the SATM. And from that assessment process, we derived what we call the science value. And at that point, our science value is directly traceable back to the Decadal Survey and quantitatively tells us whether or not we can achieve what the Decadal Survey has set out for mass change. And then that science value is used as one input into a larger value framework process that considers other parameters such as cost, schedule, risk, and partnerships. And in the end, the goal here is to identify a small subset of high-value MC observing systems. And that's going to be where we end today, is an identification of those that small subset. So I want to start with the Decadal Survey. Mass change contributes to 3 distinct panels in the Decadal Survey: hydrology and water resources, climate variability and change, and then the Earth's surface and interior. For hydrology, many of the questions that mass change contributes to is centered around the water cycle, how the water cycle is changing, and how those changes then affect local and regional freshwater availability, for instance. For the climate, mass change plays an essential role in understanding sea level rise, what's happening now, and informing future projections going forward, both for an ocean mass component as well as ice sheet and glacier contributions to sea level change and ocean heat storage. For solid Earth, mass change plays a role in understanding earthquakes as well as local sea level changes. And for local sea level, we typically think of sea level fingerprints and glacial isostatic adjustment as well as earthquake mass movement. So really a coupling of the solid Earth to water mass loading on Earth. So this is an overview graphic showing the mass change science and applications. There's a lot of information packed into this figure, but each of the specific science questions that mass change is responsive to is highlighted here. So climate variability and change in blue, the hydrological cycle and water resources kind of in white, and then Earth's surface and interior in green. And then societal applications are kind of grayed out. We also highlight the importance, and that's prescribed in the Decadal Survey in terms of the priority of that science question in terms of understanding the Earth system as a whole. So I want to walk through just a couple of these and highlight things that we've learned from GRACE and GRACE follow-on, and to give you kind of tangible examples of where mass change observations can contribute. So these are observations from GRACE and GRACE follow-on over Greenland of ice sheet mass balance, and we accumulate monthly observations, and you can see that the observations show a fairly steady decrease of about 280 billion metric tons of ice loss per year. Some years have larger melts than others. In particular, 2010, 2012, and 2019 were large mass loss seasons, and things kind of slowed down in this period. And then we went dark for about a year without observations between GRACE and GRACE follow-on. And then in terms of localizing the signals, you can see the types of spatial scales that we talked about earlier, around 300 by 300 kilometers squared. But we can see that ice loss is focused around the margins. For sea level and ocean heat uptake, this is a figure created by Steve Neeram. And you can get a lot of information when you combine satellite altimetry measurements of sea surface height in red with ocean mass measurements here from GRACE and GRACE follow-on, and then, of course, extending with mass change observations in green. You know, the sea surface height is controlled by two things. One is a mass input, which we can directly quantitatively measure with mass change, and the other is ocean heat storage. And so we can measure those with Argo floats, but also just taking the difference between these two space observing assets, we can get an estimate of ocean heat uptake, which is then an indirect measurement of Earth's energy imbalance. So the combination of these two measurements is critical for the climate variability and change panel. If we move now to the hydrology theme, and we think about freshwater storage and groundwater, this is a nice figure from Matt Rodell that came out in Nature a couple of years ago, showing emerging trends in freshwater availability, kind of the water haves and the water have-nots, and then prescribing what's driving that trend. And a lot of the reds, which mean mass depletion in this figure, are driven anthropogenically by groundwater withdrawals. And GRACE follow-on and mass change observations really provide unique information on groundwater storage change that other observations cannot. And then for drought monitoring, this was a figure just from yesterday, the U.S. Drought Monitor showing the really severe drought in the Southwest. And so this drought monitor currently assimilates GRACE follow-on data operationally, and the mass change data is unique because it quantifies dryness in the entire soil column. And I think, funny enough, we just finished processing April 2021, and Felix sent out an email today, and there was I think our GRACE data looks almost exactly like this drought map. So there's, you know, the information is right there in the mass change data. And then we move to solid Earth applications, and this is an example taken from a paper by Isabella Panay showing mass changes from the Tohoku Oki earthquake, showing a coseismic mass change when the earthquake happened, and then we can quantify post-seismic earthquake activity mass changes. In many cases, the post-seismic mass change signals are larger than the coseismic signals when you integrate them over a decade or more. So these are very important to understand, even for local sea level change applications as well. And then in this paper, there was this is a bit of a controversial result. There's been some papers that have been published that are refuting this, but they found a pre-earthquake mass change signal as well. So this is starting to think about predicting earthquakes. And then there's other topics that I won't go into more detail on, but ocean circulation, global water cycle, landscape, and then glacial isostatic adjustment, mass change plays a very critical role. And then if we think about applications, those were highlighted on the last slide. This kind of puts them into different panels. Mass change contributes to all of these areas of applications. It provides unique information for water resources, in particular in quantifying groundwater. It's the only observation that quantifies the dryness of the entire soil column for drought applications, and then that information is assimilated into a model that can downscale it temporally and spatially, along with other observations. Mass change observations can help understanding the vulnerability to floods by comparing with past measurements. JT Rieger here at JPL has done a lot of work looking at this. And then mass change data also informs agriculture, more in a supporting role than a direct role, but that information is aggregated into models that can inform crop yield forecast and look at water availability going forward for irrigation demands. For sea level, we already talked about looking at regional and local sea level, as well as predicting sea level in the future when combined with satellite altimetry measurements. And then other potential applications include earthquake hazard assessment, looking at seasonal weather prediction, as well as forest health and fire risk. And it's important to remember the Decadal Survey was really good in this, but kind of looking at the Earth as a holistic system. And so there are definite synergies of mass change with other observations here. ACCP and SBG are also observing very complementary aspects of the Earth system that can be combined with mass change data or looked at in parallel. NISAR, ISAT-2, and Sentinel-6 all provide really more highly synergistic measurements with mass change by measuring surface deformation and change, which a lot of those surface deformation signals have a mass change signature associated with them. ISAT-2 measuring the surface height over the ice sheets. Again, that has a mass change signature associated with it. And then, of course, Sentinel-6 measuring the sea surface height, which we already discussed, the synergies with mass change. So that's kind of what the Decadal Survey says about mass change. And now I want to talk about how we took that information and translated it into a science and applications traceability matrix as a study team. It involved a lot of expert interpretation of the Decadal Survey, a lot of discussions with the community, and then arriving at a final SATM. You can find it on our website right now if you want to have a more in-depth look. A few themes to keep in mind. One was the importance of continuity, which we already talked about. I already showed this quote earlier on. The second was that the Decadal Survey was really broad in what it asked for from mass change. There was a broad range of desires from kind of continuity preserving observations, like continental scale river basins, to much more aspirational goals, looking at the resolution of headwater catchments, for instance. And so the study team what we did was capture these two sets of desires as a baseline set of measurement parameters and a goal set of measurement parameters. And doing that required a lot of discussion with the community, telecons, town halls, a community workshop, and iterating on an SATM. I just want to walk you through this process because I think it's illustrative just for one objective here, H1A. This is where we want to develop an integrated Earth system analysis to close the water balance from headwater catchments to continental scale river basins. This is where mass change information comes in. And to do this, discussing synergies, we need many observations, and mass change is one of four here. Precipitation, evapotranspiration, and runoff are also needed. These are the necessary observables. what we do then is try to make an assessment of how important is mass change to achieving this objective. And we call that a utility score. In some cases, mass change plays a much more supporting role rather than a leading role. For this particular objective, it plays a very substantial role. The utility is high. The observations are essential for water budget closure. And then we derive performance targets. And here you see these are represented for baseline and goal, and we capture them in terms of a targeted spatial resolution, temporal resolution, and accuracy. And then what we call the key measurement parameter we underline, and that's the parameter in which the community would like to push. If we could improve one area of this trade space, this would be for instance, we would want better accuracy measurements. And then there's some justification for how the baseline and goal numbers were arrived at. And in the end, what we ended up with is basically a set of 15 baseball cards, we call them. This is our deck of baseball cards, and there's one card per science objective. And each one has a spatial resolution, temporal resolution, and accuracy that are targeted measurement parameters. There is a utility score assigned in the top right of each of these that tells how important mass change is, observations are to achieving that science question. And then there's a weight, and that's an importance, which is given by the Decadal Survey times the utility. And so we can weight each one of these appropriately, and that's important when we start assessing science value. The broader takeaway I want to leave you with is that for our baseline measurement parameters, these would support the full science objectives for mass change, and these are in line with the quality of measurements from the program of record. So in line with the performance of GRACE and GRACE follow-on. The next slide, this is goal. And so I can flip back and forth, and you can see for the goal measurement parameters, this is where the community would like to push, sometimes explicitly stated in the Decadal Survey, other times less explicitly so stated. And many times we've improved upon spatial resolution, sometimes temporal resolution, sometimes accuracy. So now I want to transition into architectures and technology. So the study team now needed to identify a broad subset of architectures and technology that could be responsive to the science questions and the measurement parameters established in the SATM. And one of the overarching philosophies and guidelines that we were operating by was to not point design to another GRACE follow-on immediately. We wanted to look broadly. We wanted to see if other solutions were available. And so I want to take a quick detour and go and discuss a little bit how we measure mass change in the first place. It's a very unconventional measurement. For most Earth science observations, we think about taking an instrument and physically pointing it at the Earth and probing some part of the electromagnetic spectrum, whether it be the visible or a different part of the spectrum, and maybe capturing a return signal. And mass change is fundamentally different than that. We don't point anything at the Earth at all. We just track the motion of particles. So what we can do is go back many hundred years to Isaac Newton, and he gave us this equation for gravity. So the force of gravity between two objects is proportional to the mass of those two objects and the distance between them. So if we want to measure mass, we just need to measure gravity. So we want to measure how the gravitational potential field of Earth changes over time and space. And so to do that, we can imagine putting a very tiny particle in a gravity field in a perfect vacuum. And we can say, what measurements do we need to measure the gravitational potential based on its motion? So the only force that's controlling its motion as it orbits the Earth is gravity. So what would we need? We need to build a spacecraft because we can't have a very tiny particle. And to do that, we can track the motion of that spacecraft with GPS. We put an antenna on the spacecraft. So that antenna now is no longer in the center of mass of the spacecraft, which that's what we care about. We care about the center of mass of that spacecraft. So we need to know very precisely the distance between the center of mass of the spacecraft and where that antenna is. And now we know from a lot of experience that the precision with which this tracking can be done around Earth is not sufficient to meet the science targets of mass change. We can't just track a satellite with GPS and back out mass change. We can ask ourselves the question, what if we had N satellites? You know, there are these mega constellations coming on board now. What if we had a lot of satellites? And that is one question that the mass change study did address, and we'll give you an answer to that in a few slides. So what was implemented for the GRACE and GRACE follow-on concepts is we said, well, what we can measure very precisely is the relative motion of two satellites. And we need to measure that relative motion to within a micron per second or better. Now, again, we're not tracking the motion of these two satellites relative to one another from the center of mass. That measurement is referenced to a different point on the spacecraft. So we need to know, again, the distance between the center of mass of the spacecraft and where that measurement is made very precisely. Remember, we need to make these measurements to a micron or better, so the metrology of where these instruments are aligned relative to one another is very important. And now we get a little bit more realistic and we say the spacecraft are not flying in a vacuum. There's a lot of forces acting on them, actually, besides gravity. There's drag, there's solar radiation pressure, there's Earth albedo, et cetera. And so to take away everything that's not gravity, we need a very precise accelerometer. And that accelerometer needs to be at the center of mass of the spacecraft, and it needs to be aligned within about 100 microns. And we need to maintain that alignment throughout the life of the mission. And that can be maintained using trim masses, and we can do some calibration maneuvers to make sure that the accelerometer stays aligned at the center of mass. And then the last piece of information we need to know is the attitude. What's the orientation of the satellites? That information is important for understanding the accelerometer data, as well as understanding the relative position of where the ranging measurements are made, as well as where the GPS measurements are made, all referenced to the center of mass of the spacecraft. And so the paradigm that this builds up for us is that the spacecraft really are the instrument. So when we think about measuring mass change, we think about having a spacecraft where the entire spacecraft is the observatory. And again, there's nothing looking down at the Earth, probing for mass change. We're just tracking the motion of these satellites as they orbit the Earth. And so visually, this is a movie that shows visually how the GRACE and GRACE follow-on concept works. We call this satellite-to-satellite tracking, where they are moving back and forth. So you can see here there's a mountain coming up on the right, and the leading satellite gets accelerated relative to the trailing satellite as it senses the mountain, as it feels the mountain. The gravitational pull accelerates it. And so they're constantly doing this tango, this dance back and forth while they orbit the Earth. And those very precise ranging measurements then allow us to look, not just on the surface of the Earth, but really underneath the Earth and the entire column of mass underneath the satellites that causes those ranging variations. And then we're able to understand basically how water is cycling through the Earth system, as we just showed in this animation, with water highs in blue and water lows in red. And so that's a little bit of background information about how the concept works or what we need to measure. And so now, I want to do a little bit more of a detour and say, how do we inform this trade space of what our architectures and technology we look at? We've had, close to 20 years now of observations of a single pair of satellites in a polar orbit, and there's been a lot of work done on how we can improve relative to that information. There's been significant study by the community for the last 15 plus years. And in fact, this is how I got started in the field, was looking at exactly this question for my PhD. And so there's really three ways we can improve relative to what we're doing now. One is to lower the altitude. The second is to add directionality to the observable. That includes cross-tracker radial information. And the third is to increase the sampling frequency by adding more satellites. And I'll walk you through really quickly each one of these. lowering the altitude. This one's really simple. If you fly closer to the Earth, you're closer to the source, and you're more sensitive to the gravity field of the Earth. So any changes in gravity will cause a larger distance change between the satellites. And that's illustrated in the figure on the right, where I'm showing error versus spherical harmonic degree, or kind of a spatial wavelength, smaller spatial scales on the right, larger spatial scales on the left. And you can see as we drop in altitude, we lower the error. Lowering the altitude drives, it requires a more demanding flight system. You need some sort of drag compensation system to enable extended lifetimes, because if you were not actively compensating for atmospheric drag forces, you would re-enter and deorbit very quickly within the matter of a handful of months. The second thing we can do is add directionality to the observable. There's different satellite formations that have been studied over the years. A pendulum formation provides a long track and cross track information. We have these cartwheel formations provide radial and a long track information. And then there's a two-pair bender concept where you would have a pair of polar satellites providing a long track north-south information, and then a lower inclined pair that gives you an east-west component. And the reason this is important is that due to the way that GRACE and GRACE follow-on sample the gravity field, you have very little sensitivity to east-west variations in the gravity field. And so the result of that is that any errors, almost all of our errors, accumulate and show up as stripes in our final data product. So if you downloaded kind of a non-post-processed gravity field, you would end up with something like this on the left. And the community, of course, has been very resilient and resourceful, and have developed many destriping and filtering algorithms to remove the stripes, take out the noise, but maintain the signal. Obviously, anytime you apply a filter to any signal, you can be very effective in removing the noise, but you do alter the signal content in some ways. So from a design point of view, it's desirable to mitigate or lessen the amount that you have to manipulate the data and filter it. So a pendulum pair of satellites, this would add east-west and north-south information. You could see the striping is reduced, and the same with the bender. That's the two pair, polar and one lower inclined pair. And then the third way we can improve the data products is to add more satellites. This plot right here shows the error, gravity field error introduced by each source of error on the spacecraft. I didn't say that very well, but each one of these is an individual component of error that propagates into the gravity field. And the lower it is, the least consequential it is. And the main takeaway is that the largest error source for GRACE and GRACE follow-on is not actually the measurement system, but it's something we call temporal aliasing error. So because we are limited in our space-time sampling, we cannot accurately track high-frequency mass variations good enough. So ocean tides are a great example. We know, at diurnal and semi-diurnal timescales, we have very large fluctuations of mass over the Earth, and we're not sampling quickly enough to measure them, so we have to rely on a model in the data processing to model their effect on the satellite orbits. And to the extent that those models are wrong, that error aliases into our gravity field, and that's our biggest source of error. And that's what we call temporal aliasing error. So the only way to really get around this is to either improve the models, which people are actively doing, or from a design point of view, we need to sample more frequently and directly estimate those mass variations. And so we can do that by simply adding more satellites. And so all of that background information informs the architecture and technology trade space that we examined for mass change. So we had a large subset of satellite-to-satellite tracking architectures. So a single inline pair, very similar to GRACE and GRACE follow-on, a pendulum pair, which we talked about, that adds east-west information in addition to north-south information. This is the two-pair concept where you had one pair polar and one pair lower inclined, getting both east-west and north-south information. We looked at a LEO-MEO concept where we would range from satellites in low Earth orbit to satellites in medium Earth orbit. So that adds radial information. And then we looked at in-pair small sats. So what if we could really shrink these things down, do it cheaply? You could have lots of satellites in distributed orbital planes. We looked at that. For POD, there's no satellite-to-satellite tracking. It's just measuring the position of a lot of satellites. That's what I was talking about earlier, and how those positions evolve over time. And then we looked at, this is a quantum gravity gradiometer. So this is a newer concept where we measure the free fall of atom clouds using an atom interferometer and quantum states as they orbit the Earth. And we looked at some cases there. And for all of these cases, we looked at a variety of technology options, ranging instruments and accelerometers. And I'm not going to go into detail today on the technologies per se, but there were a lot of options evaluated. And so now I want to briefly talk about science value. And I'll go through this section quickly so we can get to the results. The one impression I want to leave you with is that for mass change estimation, how we estimate a gravity field, we benefit from known satellite equations of motion. So we have an equation that we understand. We have certain things we observe. We have certain things that we model in green, and then we have something that of an unknown. And we can rewrite this on the right as just an AX equals B, where B is our observations, X is our state parameter of unknowns, and then A is a matrix of partial derivatives that provides an analytic mapping between the observations and the state parameters. So we can do a formal inversion. We can get a formal estimate of errors from the gravity solution. And so we leverage this for MC. We ran these high fidelity numerical simulations. We call it an AUSSIE. We leveraged Grace and Grace follow-on software. And it's a fairly heavy lift computing wise. I think we logged about 500,000 CPU hours, stored a lot of data. And I got in trouble for that. My colleagues, some of them on the line, were yelling at me to delete data because I was hogging the machine. But we're past those points now. So, and this is an overview of how the AUSSIE works. We basically create a simulated world that has all the mass transfer processes in it. We sample it twice. One to create a truth set of observations and one to create a nominal set of observations. So that's simulating orbit initial conditions, simulating the measurements that we want to take, and then we add noise to this nominal set of observations. So temporal aliasing error model, this is the geophysical model error for high frequency mass variations, and then also instrument noise, so ranging noise, accelerometer noise, etc. And from this information, we can then do a rigorous estimation of our simulated world, and we can compare our simulated world estimated to the truth to get an estimate of error. And that estimate of error, I'll show you here, we can map it across space and time, space on the x-axis, time on the y-axis, and we map error across this entire domain so we can get a really holistic view of the performance of an architecture across the space-time domain. And these techniques, we published a paper on this last year in Earth and Space Science. This was led by Marcus Hawk, who just finished his PhD at the Technical University of Munich. So this is a nice framework because if you remember our science SATM, we also couched in terms of spatial resolution, temporal resolution, and accuracy. And that allows us to really one-to-one overlay a target with the performance of an architecture, and we can nicely have a very easy formula where we can say a science value of a particular objective is some weight 1 up here times a target 10 divided by 4. If we go to this point in space and time, we can assess the error of this architecture, and we can get a number, a quantitative number for the science value. And we can do this for all of the different science objectives, all 15. We've summed them up and we normalize by the weights. And I'll just go to the punchline here. When we do the normalization, we end up with an approach where a value of 1 means that we've satisfied our baseline objectives. And then we can actually understand these science value scores going up. There's no hard cutoffs. It's a gradual escalation of the scale. So here, like a factor of 3 actually physically means that we've improved some combination of spatial resolution, temporal resolution, and accuracy by a factor of 3. And those improvements have been happening on the parameter of interest where the community has said that they would like to push and improve. And we have the ability to assess our goals. So let's go to the results. These are the value framework process and the high value MC observing systems. So right away, I'll cross a few of these off. So POD, we determined through simulations that it had still too low of a science value, even with lots of satellites. For the gravity gradiometry, this has a low TRL and long path to development. And these were validated through both an instrument and a mission design lab for this technology run at Goddard. The LEO-MEO concept, so that was the tracking between low Earth orbit and medium Earth orbit, had low science value, and also several technical challenges were identified by the team. And then the small sats, we ran a TMAC session at JPL, and we found that the design was simply not cost effective. I mean, if you remember, the paradigm of this observation is really that the satellites are the instruments themselves. So we do need very strict thermal control and alignments and knowledge of center of mass, et cetera. And we found through the TMAC session that did not scale in terms of cost as one would kind of need for a constellation of small sats to be effective. And so this is a high-level overview, science value scores on the y-axis, cost on the x-axis, the full trade space of architectures looked at. So here's POD down here, low science value, it's below 1, which would indicate our baseline science objectives have been fulfilled. We can see where the gravity gradiometry lands depending on the altitude that it's flown at. And then there's these different families of architecture, single inline pairs, some pendulums, some benders up here in the triangles, LEO-MEO tracking. And so after we prune this based on the architectures that were pruned, like we discussed, and we've also pruned based on technologies, and I didn't focus on this a lot in this talk, but for the ranging system, we've pruned such that we prefer the LRI due to the successful technology demonstration on Grace follow-on. And then electrostatic accelerometers, that's a conventional technology that's been used on Grace and Grace follow-on. Those were identified as having the highest technology readiness level. Although there were 3 other accelerometer types that are still considered as possibilities for technology demonstrations. It's a gravitational reference sensor that has superior performance over electrostatic technologies, an optomechanical inertial sensor that has a little bit worse performance, but it's really small. It has very favorable size, weight, and power characteristics. And then there's quantum-based technology that could be a very nice demonstration for the quantum-based technologies. And so from this trade space now, we want to prune a little bit further. And so we look at continuity with Grace follow-on. If you remember, the Decadal Survey was very clear in the importance of continuity. And we did that in a few ways. We looked at the Grace follow-on lifetime estimate for the reliability of the spacecraft, as well as the orbit degradation. The orbits of Grace follow-on has very limited orbit maintenance capability. So the way the mission's supposed to work is that the satellites naturally degrade through the atmosphere, and eventually they will re-enter. So we looked at both of those aspects, and then we overlaid a schedule S-curve. So how long will it take to develop and launch each of these different architectures? And we want to see, kind of where these crossing points are. And so this is a plot on Grace follow-on orbit lifetime and expected reliability. It's a bit busy, but the magenta curve on the left here, this is the altitude of the Grace follow-on satellites and a prediction based on the latest solar cycle 25 prediction. Now, solar cycle 25, it's supposed to be pretty benign, like 24. And so that's advantageous for having GRACE follow-on have a longer orbit life. Of course, if cycle 25 is more, has more activity, then the orbits would decay faster. There's a lot of uncertainty in that. The dashed blue curve provides an estimate of spacecraft reliability. So to get that, the team looked at a historical database of similar kind of spacecraft and fit a Weibull distribution to when those spacecraft failed. And we find, a 50th percentile of reliability here in 2028, 70th percentile in 2025. So a takeaway here is that the GRACE follow-on lifetime is more likely to be limited by system reliability rather than orbit lifetime. And so when we overlay that with the schedule estimates, we take these schedule S curves and look at the 50th percentile launch readiness date. Unsurprisingly, a single inline pair very similar to GRACE follow-on has the quickest development time, followed by a pendulum and a bender. And so here in 2028, the expected GRACE follow-on reliability is at 50%, and then it falls beyond that as we push to the right. So we identified architectures that were compatible with having the highest likelihood of maintaining continuity with GRACE follow-on, and also improving science. So architecture A here, this is basically like GRACE follow-on, except it has LRI as the primary ranging instrument. It would remove the MWI. And then architecture B, C, and D all add elements to architecture A. So the implementation could be staggered in such that architecture A could launch first. And then for architecture B, you bring a third satellite along to complete this 3-satellite pendulum motion. And then for architecture C and D, you could bring along an incline, a second pair of satellites at a lower inclination, and those could join the constellation at a later time. And then we note that architecture A, B, and D are all the most compatible with interest from our international partners. And so I'll show a little clip. This is architecture A, so you can visualize how this looks like. This is ranging in the along track direction polar orbit between a pair of satellites. So this looks very similar to the GRACE and GRACE follow-on concepts. And if we go to architecture B, it's hard to visualize what the pendulum motion is, but this is spacecraft 1 and 2 are ranging between each other. And then spacecraft 5 appears to do this pendulum motion relative to that pair, and it's ranging between spacecraft 2, bringing in that east-west information. And when you do that, you can see the improvement in science value, also the increased implementation cost. And then the architecture D, this is 2 pairs. In this architecture, there's 2 distinct pairs of satellites, 1 and 2 ranging between each other, and 3 and 4 ranging between each other. And here, the architecture implementation, the 2 pairs of satellites are really decoupled from one another. The connection primarily happens in the ground in the data processing. You can design the orbit such that they are coordinated in terms of how the ground tracks evolve. That is a parameter that can be studied going forward into pre-phase A, but there's no strict requirement that must be the case. So what can we expect scientifically from these 3 options, architecture A, B, and D? Architecture A is what we're used to with GRACE and GRACE follow-on. As we move to the right, we can think about improving spatial resolution down to 235 square kilometers or 200 square kilometers. Architecture D also improves the temporal resolution, going here from monthly to biweekly because we have two pairs of satellites, and that leads to a significant enhancement in applications. And on the bottom, you can just visually see how the picture kind of becomes more clear. This is a truth synthetic signal that we simulate, and this is what we recover with these various architectures. And you can see how the image gets crystallized some going from A to B to D. And then this is a bit of an eye chart, but we can go through, and depending on your field of interest, different areas where architecture A represents kind of the current state of the art, And then if this is the highest performing architecture we think would be reasonable for mass change, likely it could fall somewhere below that and the final implementation, depending on final altitudes, et cetera. But we can think about, improving or resolving individual ice sheet drainage basins and glacier systems to support their modeling and prediction, closing the water budget at smaller spatial scales, and that will improve data assimilation into hydrology models. We can improve our understanding of ocean atmosphere heat fluxes because of the smaller spatial understanding of mass and steric sea level change signals. Also, frontal position separation of the Antarctic circumpolar current. We should be able to detect smaller magnitude earthquakes with this architecture. And then, the improved latency and resolution would benefit applications significantly. So the path forward, MC is really poised to continue building the climate data record established by Grace and Grace Follow-On. The study team has identified architectures that maximize the probability of maintaining continuity while also improving upon the quality of the data products. We're currently in the process of transitioning to pre-phase A. In this next phase, the mission concept will be further refined. We'll go into further in-depth study of high-value architecture variants. And this third bullet is critical. We'll continue engagement with the international space agencies to further refine the observing system and work-share possibilities. One thing, our estimated costs are beyond the Decadal Survey cost target for mass change. And so international collaboration is a key aspect for mass change going forward. And our notional targeted launch date that we would be working to right now is nominally 27 to 28 for implementation, at least of the first elements of the observing system. And I believe that is it.
Thank you, David. That was great, super comprehensive. We have time for some questions. There was already a little bit of back and forth in the chat originating from a question from Evan. Evan, do you just want to ask your question? If not, I can just, Evan?
Sometimes we have audio issues.
Okay, so I'm just going to read the question from Evan to you, David. It wasn't specifically said oops, now the chat jumped and I lost the question. If the retrieved parameters in the OSSI are the coefficient of the spherical harmonic expansion of the gravity field, if so, what is the error contribution from locating the mass anomalies from the gravity anomalies? It wasn't clear to me, Evan, if you meant like in the horizontal or vertical.
He means in the vertical.
In the vertical. Oh, okay.
Yeah, that's a challenge. We really have no ability with the mass change observation to disaggregate vertically. So we have to bring in ancillary information, either models or other observations to, say what's groundwater versus surface water versus atmosphere, et cetera.
Right. Yeah, there's already quite a bit of back and forth in the chat on that. So I think, are there any other questions? You can just unmute, go ahead and ask it. Cedric, I see you have your hand raised.
Yeah, hey, David, that was really awesome. I particularly thought that some of the animations you had at the end were really striking and kind of give an idea of what to expect from the various architectures. So really well done. Hey, listen, I guess my question is, so it seems, at least my understanding of what you presented is that there may be like an initial launch of something that looks like Grace Follow-On and followed by perhaps another one or two launches. And that is kind of reminiscent of the Sentinel approach to launching satellites. And I guess, has this been done by NASA before? And, what do you expect might be a challenge there?
Yeah, it's a good question. I think that staggered implementation approach is definitely a possibility going forward. From NASA's viewpoint, we definitely think continuity is quite important. So having that earlier launch date is viewed favorably. I think it depends on how the conversations go with the international partners, ESA, DLR, and CNES. ESA is in particular, they have a phase A study ongoing. Actually, I think it just kicked off now. And there's a kind of a deadline. They have a ministerial meeting at the end of 2022, whether they would get approved for a full mission implementation. And that could be a scenario where we could have 2 pairs of satellites, but the development time of that other pair could be longer than the initial pair. For a Sentinel implementation, there's no such discussions, on NASA's side. I think, from ESA, from what we hear, there's desires to get mass change into the Sentinel type program. So this could be kind of a proving ground for observations that would contribute to applications in a way where Sentinel could pick it up. That could be a long-term goal, but it's really kind of a little too far-reaching, to make decisions based on that, let's say. But that's in the discussion.
So,
thanks so much.
David, can I add a comment there to Cedric?
Oh, absolutely.
That in the ocean altimetry world, we began with Topex Poseidon. We had a series of JSONs, and now we have Sentinel-6 Mike Freilich. So there's been a path from doing missions with partners, and then transitioning to an operational Sentinel. I think I don't know if that addresses your comment or your issue you were raising, Cedric, but I thought that's what I heard. You're asking if there was an example of this.
Well, let me clarify. No, I guess what I was thinking about is how, they might launch Sentinel 3A 2 years before they launch 3B. And together 3A and 3B are, providing a lot of value. And it's what I was seeing in the potential scattering of launching various satellites, as you have like different phases of the mission where in one phase you have more satellites than another.
Okay.
There was one more question in the chat that we could just get to before we kind of run out of time at the top of the hour. Victor, you had a question. Does the distance between antenna, I'm not sure if you mean GPS antenna or KBR if we have one, and the center of mass change with temperature? How do you keep track?
Yes, it does. And so I think that's important. It doesn't change to get out of the, there's the alignment requirement with the accelerometer. It does, and that just folds into the data processing. We continually track the center of mass on the spacecraft using calibration maneuvers, and we have trim masses to move and maintain the center of mass with the accelerometer. But temperature dependencies are an important aspect, and that's actually, that's one reason why the study team found the small sats would be challenging.
Yeah, thank you, David. I want to kind of honor the schedule and people's commitments to other meetings that probably start at 10. We are almost at 10 o'clock, so I just want to thank David for the talk and everyone for attending. Maybe if there are more questions, those who want to can stick around and unmute and ask their questions. Otherwise, we'll close the official part of the talk here. Thank you so much, David.
Thank you.
Thank you, David, and thank you, Felix, for hosting. We appreciate that. Have a nice weekend, everybody.
All right, thanks. Yeah, I guess if we have questions, we can just email David.